Hi, Mr. Crone here again with another video in my conceptual series, and in this video we're going to look at some of the other acceleration equations. So in the previous video we defined acceleration and looked at the units and some of the aspects of its direction, but we didn't talk about the displacement, and so this time we'll sort of deal with how do you find the displacement, and there's actually several different ways to do it. But before I show you the equations that involve displacement, let me just show you another way that we could use the acceleration equation. So it was defined as simply being the change in the velocity, which is v minus v naught, divided by t. But oftentimes, in fact, I would say one of the most useful ways to use this equation is to solve for the final velocity. So if I knew, for example, what the acceleration of a person was, and you tell me how long they accelerated for, I should be able to use this equation to find the final velocity. Now we could also solve it for the initial velocity, or we can also solve it for the time. But what I'm going to do is make just a couple of algebraic steps. I'm going to multiply both sides by t, but I'm not going to write that that's what I'm doing. I'm just going to do that in my mind. I'm going to multiply both sides by t. The t's will cancel over here, and I'll end up with at equals v minus v naught. And then we'll take the v naught. We need to undo that. So the way we would undo that subtraction is we would do addition. So then I would add that over to the other side, and I would get at plus v naught. And that is a very useful version of this equation. Make sure when you make the t's for your time that they're curly so as not to be confused with the plus sign. When we were just talking about velocity by itself, we didn't have to worry about, it was a much simpler formula. But now we're going to be dealing with the plus sign in several of the formulas we have, and also time is in there. So you want to make sure it's really clear the difference between those two. So this is one of the acceleration equations that you'll be able to use, and the way I would argue it is this. If you want to solve for the acceleration, then this is obviously your formula. There's no algebra to do. You just plug the numbers in, you spit out the answer, you put the correct units with it. This equation would work very well if you were looking for the velocity, because it's already solved for v. I've already done all the algebra for you, and so therefore you just got to plug in the numbers and you spit out the answer, whatever the calculator says. But if you want to solve for the time, or you want to solve for v naught, I'm not going to write every single version of the equation because you should be able to do that algebra. This is definitely very doable for any high school student to be able to solve this. And what I would recommend is that the easiest way probably to do it is to write the equation and then just plug in all the numbers on the line underneath it. So if I was, for example, maybe I have the final velocity and I have the acceleration and I have the initial velocity, but I want to know how long did the acceleration last for. So in that case, I would plug in the v, the a, the v naught, and then I would start to do the math. There would be a number replacing this v naught, and so then I would be able to start moving the numbers around just by kind of doing the math. It sort of reduces the algebraic requirements so that you don't have to do so much algebra. And so I would argue that you would use this equation only if you solve for acceleration, and anything else I would use this equation. Because essentially this equation is making that first algebra step for you, and then you just have to finish up the last step or two to get either t by itself or to get v naught by itself. V naught's very easy because all I would need to do is to subtract the at. If I subtract this guy, he moves over to the other side. I get v minus at, and I've got v naught. Okay, so that's actually the old equations. So now let's talk about some of the new equations. How can we find the displacement if we have an object that is accelerating? Well, in the old days, we would have done this. We would have simply said that the displacement is going to be the velocity, the average velocity, times however much time has gone by. But there was a condition for that, and that is that it must be constant velocity. So that equation, if you want to know what your displacement is, you would just multiply the velocity by the time and you would get the answer. But there's a little bit of a problem, and that is that if your average velocity, if the velocity you're traveling at is changing a lot, then your average velocity might not really be a good representation of what actually happened in that motion. So if the velocity is not constant, then what you would have to know is that the velocity changed smoothly from one velocity to the other. And then if that was true, we could use this equation. This is a formula for the average velocity, but it only works when you have a smooth transition from the initial velocity to the final velocity. And then if that's the case, then we can just add the two together and take the average the same way we would take any average. We would divide by the number that we had added together. So we added two numbers together. I'm going to divide by 2, and that will give me an actual answer that's valid. Now, if the transition is very unsmooth, so imagine if a feather was falling. Well, feathers don't accelerate very smoothly. They kind of speed up and then slow down. They kind of flutter as they fall. And so this equation would not be valid for that. So this equation must have constant, but this time it has to have constant acceleration. So it has to change its speed smoothly from one speed to the next. And then this will give the correct average velocity. And since it does give the correct average velocity, we can make a substitution. So for this average velocity, I'm going to plug in the v plus v naught over 2 into that equation, and that's going to give us a new version of this displacement equation, which will actually have the two velocities. So the two velocities from the motion, the one at the beginning and the one at the end, that will now be in the equation for displacement, and we will end up with this equation. Let me put the word substitute. So making that substitution, we would end up with the equation d is 1/2 v plus v naught times t. So now we actually do have an equation that will allow us to figure out the displacement from just knowing the velocities and the time without even knowing the acceleration. Without even using the acceleration, I can figure out what the displacement will be. But there are times where I might know the acceleration, and maybe I don't know both of the velocities. And so what I'm going to do right now is make a couple more substitutions, and the only purpose of this is just to create new versions of the equations so that we can go to the answer in one step. We can look at what we just did right now. Imagine that you have the two velocities and the time. You said, oh, well, for this equation, what I need is the average velocity, but I don't have the average velocity. Well, but I can calculate the average velocity with the two velocities here, and then take those two velocities and plug them into this equation and multiply them by the time, and then I would be able to get the displacement. But what this equation allows us to do is to do it without doing it in two steps. So instead, we only have to use one step. If I have the two velocities and the time, I can calculate the displacement in one step by just simply plugging into this equation. Or I could use this equation to find, for example, the final velocity, or maybe how long did it take for this acceleration to occur by solving for t, or solving for the final velocity. So I can use this equation to find the displacement, but I could also use this to find any of the other properties that I see that are inside this equation. So what we're going to do right now is we're going to combine the two equations that you see in the boxes. We're going to do a couple different substitutions and just create more equations so that we'll be able to get the answers to these problems a little bit more quickly by making one-step calculations instead of having to constantly keep doing things by two-step calculations. So let me write the two equations. Let's move this guy up just a little bit. And let's write the two equations. So equation 1 was v equals at plus v naught, and the other equation was d equals 1/2 v plus v naught t. And the first substitution I'm going to do is going to be very simple. I see v is in both equations. So I'm going to take this guy and substitute that in for that v right there. Okay, and when I do that, I'm going to do a little bit of algebra, so I'm just going to kind of clean it up just a little bit for you. But when I make that substitution, it creates this equation that says the displacement would be 1/2 at squared. Notice that I have at, and it's going to be inside the parentheses, so that's going to become at squared. But then I also have v naught, so that v naught is going to become plus v naught t. This is our third equation. And what's different about this equation is that there is no final velocity. If you noticed, each of the equations that we were looking at before was missing one of the variables. So for example, the previous equation was missing the acceleration. That doesn't mean it's not accelerating. It is accelerating because I have two different velocities, but I just don't know what the acceleration is. I haven't calculated it. And if I'm not being asked for the acceleration, then don't calculate it. Use this equation instead. So instead of making a two-step problem, you just be able to do this in one step. This equation is missing a, What's this guy missing? Well, we already know that. This is the whole point of this video, is it's missing d, the displacement. And so each equation is always missing one of the variables. And that's why we need different equations. Depends on what given information that we had as to which equation is going to allow us to solve that problem in the easiest, least number of steps. We'll be very efficient with the way that we solve the problems. I do want to make one more substitution here. I'm going to actually solve this equation for t, just so that I can make the substitution a little bit easier. If we were to solve this for t, that would say that t is equal to v minus v naught over a. And if I take that same equation, d equals 1/2 v plus v naught t. Now I'll make this substitution. I'll substitute the v minus v naught over a for t, and then you'll see that I'm going to have v plus v naught times v minus v naught. So that's going to end up giving me v squared and v naught squared, but the middle terms, right, if you do FOIL, first, outer, inner, last, the outer and the inner are going to be minus v naught v and plus v naught v. So they're actually going to cancel out, and they'll just disappear. But what we will be left with is the following equation. V squared equals v naught squared plus 2ad. And that is our fourth and final equation. Okay, so for me, the way I learned these, I kind of learned them all at once, but I do feel like there's a lot of power in really getting familiar with the first equation, really understanding what acceleration is, and then bring it to the more complicated equations. Clearly, these are more complicated equations. So nobody's going to be asked to do these right away, but there will be some expectation that you will begin to get familiar with these, starting with the level 1. The level 1 equations. And there are two versions of the same equation. So that is a is equal to v minus v naught over t. That's our definition for acceleration. And then I rewrote this as v is equal to at plus v naught. If you're solving for a, you use this guy. If you're solving for anything else, start with this. This just takes you one algebra step ahead so that it'll be easier for you to get to the final answer. Once you master that, you know how to do that, then you would move on to level 2. And at level 2, then you would be asked to show that you can use the equations that involve the displacement. And so that would be d is equal to 1/2 v plus v naught t. D is equal to 1/2 at squared plus v naught t. And then finally, v squared equals v naught squared plus 2ad. So at level 2, you'll get familiar with these equations, and once you've mastered all of these, are called the kinematic equations. The kinematic equations. And once you've mastered these, then we can start to think about things like, for example, gravity. Gravity is a very interesting form of acceleration because we all experience it all the time. And so we're very familiar with it. We kind of understand it a little bit. We know if we jump down, we feel that picking up that speed. And so all we're going to do at level 3 and level 4 is start to look at the graphical versions, the graphical representations of this motion. And then you're also going to be asked to deal with gravity. First in very simple ways, and then as you reach the highest level at level 4, you're going to be asked to deal with things where we throw something up in the air and then it comes back down and lands back in our hand. That's going to be the highest level. All right, so in the next video, we'll take a look at some of those more complicated problems.